Hello everyone, today we want to talk about 8.9 improper integrals. The improper integral is used for cases in which the interval of integration is infinite, or the integrand has an infinite discontinuity on the interval of integration. So in this lecture, we will talk about the first case when the interval of integration is infinite. So let's take a look at page 2. In example 1, right here we want to evaluate the integral 1 over x squared plus 1 from 0 to infinity. So right here you can see that the interval of integration is infinite, from 0 to infinity. Okay, so in example 2, you want to integrate e to the negative 3x from negative infinity to 0. And you can see that right here, the interval of integration is also infinite. Okay, so today I want to talk about the improper integrals for cases like this. So let's take a look at the idea. We know that infinity is not a number, so basically we cannot plug in infinity, okay, just like what we used to do for fundamental theorem of calculus, right? We say that if you want to integrate f of x from a to b, you need to plug in, after you found a antiderivative, you need to plug in the upper bound, plug in the lower bound, and find a difference, right? But here, let's say your upper bound is infinity, like this. You cannot really plug in infinity. Okay, so what should we do? So here's the idea. We want to integrate f of x from a to b. Okay, just like normal integral. Okay, we do a and b, both a and b are just numbers. Okay, of course, right here we want b to be greater than a. Okay, now the idea is to fix a, so a is fixed, and then increase the value of b. So for example, I can integrate this function from 1 to 2, and then integrate this from 1 to 3, integrate this from 1 to 4. Okay, and we keep increasing the value of b. And eventually, we will let b go to infinity. Okay, so that's the idea. Similarly, if you have an integral from negative infinity to some number, we can fix the upper bound b and then decrease the value of a. For example, you can integrate from negative 2 to negative 1 and then decrease the value of the lower bound. You integrate from negative 3 to negative 1, negative 4 to negative 1, and eventually we will let a go to negative infinity. So that's the idea. Okay, so let's take a look at the boxes below. If your function f is continuous on the interval from a to infinity, so take a look at the first picture from a to infinity, then we will need to integrate f of x from a to b instead, because we can plug in the upper bound b. Okay, after we find the antiderivative, we plug in the upper bound b, we plug in the lower bound a and find the difference. Okay, and then we will increase the value of b. With that, b go to infinity. Okay, so we take the limit when b goes to infinity. Similarly, if you want to integrate, okay, if you want to integrate from negative infinity to b, okay, that is the case when f is continuous on this interval from negative b to a. From negative infinity to b. Then we will need to integrate f from a to b as well. And then with that, a go to negative infinity. Okay, again, the reason we use the integral of f from a to b is that if a and b are both numbers, we can plug in the upper bound and lower bound by using the fundamental theorem of calculus. Okay, but if you have infinity and negative infinity, okay, they are not numbers. You cannot just say, hey, let me plug in infinity. Okay? Now finally, if your f is continuous on the interval from negative infinity and infinity. And basically, you will do the same thing right here. Okay, you want to increase the upper bound and you want to decrease the lower bound at the same time. Okay, so right here we will need to split. Okay, we will need to split this integral. So from negative infinity to infinity, we can always find a number in between, right? For example, you can find 1. 1 is between negative infinity to infinity. Or you can find 0. 0 is between negative infinity to infinity. And why do we want to find a number in between? This is because we need a number. Okay, so see here, when b goes to infinity, a is fixed. When a goes to negative infinity, b is fixed. Okay, so we want to find a fixed number. Okay, so right here, let's choose c. C is any number you like. Okay, you can choose 2, you can choose 7, you can choose pi. It doesn't matter which number you pick. Okay, so once we pick that number, we can rewrite this integral as the integral of f from negative infinity to this number c, and then add the integral of f from c to infinity. Okay, from c to infinity. Okay, and of course, for the first integral from negative infinity to c, we will need to use item 2. Okay, so use item 2. And for the second integral, the integral from c to infinity, we will need to use item 1. Okay, so whenever you have an improper integral, the first thing you want to do is to rewrite your integral. Okay, rewrite your integral using the limits. Okay, next, the improper integrals are said to be convergent if the corresponding limit exists. Okay, so notice that right here, as I mentioned earlier, the first thing you want to do is to set up a limit, right? So that means eventually you will need to evaluate the limit. Now, if the limit exists, we say that the improper integral is convergent. Okay, now if the limit does not exist, then we say the improper integral is divergent. Okay, so let's make a quick review. When we say a limit exists, we mean that we can find a specific value. For example, the limit equals 0, the limit equals 1, the limit equals pi, the limit equals negative 10. Okay, we can find a specific value. Okay, if you can find a specific value, the limit exists. Now, if the limit goes to infinity, or if the limit goes to negative infinity, or we don't even know how to evaluate the limit, okay, then the limit does not exist. Okay, so let's take a look at examples on the second page. We want to evaluate this integral. Okay, 1 over x squared plus 1 from 0 to infinity. So notice that you see infinity in your upper bound. So that means this is an improper integral. Okay, this is an improper integral. So let me write down the integral of 1 over x squared plus 1 from 0 to infinity. And we say that the first thing you want to do is to set up the limit. So you want to set up the limit of the integral of 1 over x squared plus 1 dx. So notice that infinity is not a number, so that means you want to change this. Okay, change this to some, you can use b, okay, but let me use t right here. Okay, and 0 is a number, so don't worry, just put 0 right here. And then you will take the limit as t goes to infinity. Okay, change this infinity to t, and that t go to infinity. Okay? Now, since this integral right now is from 0 to t, t is just a number, we will be able to evaluate this guy. Okay, so let's keep the limit notation right here. We will need to evaluate this limit at the end. Okay, so let's take care of this integral first. So what is the integral of 1 over x squared plus 1? Now if you remember from Calc 1, this is arctangent of x. Okay, now if you forget, then you may use trig sub right here, because x squared plus 1 is of the form x squared plus 1 squared, right? So that means your x is tangent theta. Okay, so you can try trig substitution right here, or simply remember that we learned this from Calc 1. The integral of 1 over x squared plus 1 is arctangent of x. Okay, arctangent of x, and from 0 to t. Okay, from 0 to t. Now remember, 0 and t are both numbers. That means you can plug in the upper bound, plug in the lower bound. Okay. Now you might be wondering, wait a second, do I really need to write down the limit? Can I just write infinity right here and plug in infinity? The answer is no. Okay, because infinity is not a number. You cannot just plug in infinity. Okay. So right here, let's keep the limit notation. We plug in t, so we have arctangent of t, okay, minus, plug in the lower bound, arctangent of 0. Okay, arctangent of t minus arctangent of 0. Okay, now you will need to evaluate arctangent of 0, and from pre-calculus we know that this is 0, right? This is 0, so basically you minus 0. Okay, so we will take care of the limit of arctangent of t as t goes to infinity. Now this is also from pre-calculus. Okay, now if you forget, just remember, just recall that the graph of arctangent, okay, is this, and there are two horizontal asymptotes for arctangent. So when x goes to infinity, your y will approach pi over 2, and when x goes to negative infinity, your y will approach negative pi over 2. Okay, so the two horizontal asymptotes are y equals pi over 2 and y equals negative pi over 2. Okay, so right here, when t goes to infinity, infinity is in this direction, right? Infinity is that way, and your y will approach pi over 2. So that means the limit of arctangent of t as t goes to infinity is pi over 2. Okay, and finally, don't forget to write a sentence. Okay, I know this is a multiple choice question, but let's say we have a free response question. Okay, you want to write a sentence to answer the question, to describe what's going on, what are you doing here. Okay, so thus the improper integral (0 to infinity 1 over x squared plus 1 dx), okay, is convergent to pi over 2. Okay, now of course right here, if you want, you can use the verb converges. Okay, from converges to pi over 2, or is convergent to pi over 2. Okay, so notice that right here we take the limit, so that means this value, okay, the value of the integral, okay, will approach pi over 2. So we use 2. Okay, so this value will approach pi over 2, converges to that number. Okay, because in the past a lot of students wrote down at. Okay, I don't know why, but this really not something you evaluate at some x value. No, it's not at. It's convergent to that number. Okay, converges to pi over 2, so you will need to choose B, I believe. Okay, now notice that pi over 2 is a specific number. Okay, so that's why we say it converges or it is convergent. Okay, because pi over 2 is a number right there. Okay, so let's take a look at example 2. We want to evaluate the integral e to the negative 3x from negative infinity to 0. Okay, and you see negative infinity, so you know it is an improper integral because the interval of integration is infinite. Okay, so let's write this down. Remember, the first thing whenever you see an improper integral is to set up the limit. Okay, set up the limit. And notice that right here, your upper bound 0 is a number, so just put a number right here. And your lower bound, negative infinity, it's not a number, so you want to change it. So let me change it to t. Okay, and then you will take the limit as t approaches negative infinity. Okay, negative infinity. Okay, so let's keep the limit notation. Now, there's a common mistake in the past is that students don't like to write down limit notations. Okay, so that is not correct. Okay, remember you need a limit notation. Okay, because it reminds you at the end you will let t approach negative infinity. Okay, so that's the key point. Okay, that's the key point. Okay, so now, okay, now t and 0 are both numbers, right? So we can evaluate this integral just as we did in the past. What is the integral of e to the negative 3x? It should be e to the negative 3x and divided by negative 3, right? So you have negative 1 over 3. Okay, because of the chain rule, when you take the derivative, you have to multiply by negative 3. That means when you integrate, you need to divide by negative 3. Okay, from t to 0. Okay, from t to 0. So notice that right here, this is my personal preference. You don't have to follow. You don't have to follow it, but negative 1 over 3 is a constant, so let me put it down. Okay, I like to put all these constant multiples out, so that won't mess up with my calculation. Okay, so I will need to multiply the whole thing by negative 1/3 at the end. So the negative 1/3 limit t goes to negative infinity, and now we have e to a negative 3x. Okay, e to a negative 3x, and right here you can write it as 1 over e to the 3x. Okay, 1 over e to the 3x, because that negative exponent means it's the reciprocal of e to the 3x. Okay, sorry, from t to 0. I forgot t to 0. And now you can plug in the upper bound. So that's e to the 0, and plug in the lower bound, e to the 3t. Okay, and we know that e to the 0 is 1, right? So we have 1 minus 1 over e to the 3t. So right here, you will need to evaluate. Okay, you will need to evaluate the limit of 1 over e to the 3t as t goes to negative infinity. Okay, now notice that this is also from pre-calculus. Okay, so that's, you can see that why we need prerequisites on this course, right? Because we need a lot of things from before. Okay, it's not just calculus 2. You need everything from like high school algebra, pre-calculus, and calculus 1. Okay, so this is the graph of y equals e to the x. Now, if you multiply by 3, basically you just need to stretch, okay, or shrink. It depends on this number, the graph of e to x horizontally. Okay, so if you have 3, you multiply by 3, that means you need to shrink this graph horizontally. If you have 1/3 x, then you have to stretch it. Okay, so this is the graph of y equals e to x. You can call it the parent function, and e to 3x will will be similar to this graph. Now we want t goes to negative infinity, and notice that negative infinity is in this way, right? Approaches the left, right? So that would be negative infinity. So you can see that right here, your y value will approach 0. Okay, your y value will approach 0. Okay, we know that there's a horizontal asymptote for y equals e to x, which is y equals 0. Okay, so it will approach 0. Okay, so I'm not plugging this, I just take a look at the picture. So it will approach 0. Okay, but it will never be 0. Okay, so right here you can see that this is a very, very small number. Okay, it will approach 0, but it will never be 0. And then you divide 1 by a very, very small number. Okay, for example, if you divide 1 by 0.1, you get 10. If you divide 1 by 0.01, you get 100. If you divide 1 by 0.001, you get 1,000. Okay, but now you divide 1 by like 0.0000, like a billion 0 and then 1, right? It will be really, really large. Okay, now of course the example I was talking about is not small enough. You will need to find even smaller number right here. Okay, so that means 1 over e to the 3t will be even larger. Okay, so you can think of this as infinity. And 1 minus infinity is negative infinity, right? 1 minus infinity is negative infinity. And negative infinity multiplied by negative 1/3 will be infinity. Okay, so right here you have infinity. Okay, now another common mistake students made in the past is to write down something like this. Okay, now notice that this is not correct. Okay, this is not correct. First of all, you cannot divide by 0, right? We don't allow 0 to be in a denominator. Okay, you cannot do that. And then infinity is not a number. You cannot really operate it. Okay, so previously when I explained it, okay, it seems like I was operating infinity. Okay, but what I'm really doing is to take the limit. Okay, so you can if you want, you can write this on your scratch paper. Okay, if that helps you understand better, you can definitely do it on your scratch paper. But do not write this as your work. Okay, so right here you can see that right here I evaluate this directly and get a result as infinity. I didn't say, yeah, I need to write down everything in detail. No. Okay, because this is not correct. Okay, you cannot operate infinity. Okay? Okay, so is infinity a number? No, infinity is not a number. So right here, your limit is not a specific number. So that means the limit does not exist. Okay, so meaning the limit does not exist. Okay, so therefore, the improper integral e to the negative 3x dx from negative infinity to 0. If the limit does not exist, we say that the improper integral diverges. Okay, diverges. Of course, if you want, you can use the term is divergent. Oops. Okay. Divergent. It's okay? So a quick summary. When you see infinity or negative infinity in the bounds, you know it's improper. And the first thing you want to do is to rewrite your integral using limits. So you want to change this infinity to some number. Here you can use t, you can use a, you can use b. Okay, just don't use x. Okay, you can use anything you like instead, just except for x. Okay, and then you will let t in this case go to infinity. You will let t in this case go to negative infinity. Okay, and then perform your integration as before. Okay, just like in Calc 1, or we learn a lot of integration techniques, right? So integrate as it is proper. Okay, and eventually you will need to evaluate the limit. Okay, now if the limit is a specific number, then we say the improper integral is convergent, and it will converge to that number. Okay, so right here it is a specific number. The improper integral converges to that number. Now if the limit does not exist, then we say the improper integral diverges. Okay, so let's take a look at the next page. We want to talk about a comparison test for improper integrals. Okay, so right here, suppose the functions f and g are continuous functions. They are continuous on the interval from a to infinity. Okay, and right here, f is greater than or equal to g, and g is greater than or equal to 0. Okay, this means the graph of f is greater than or equal to means it's above the graph of g or on the graph of g. And right here, greater than or equal to 0 means above the x-axis or on the x-axis. Okay, so greater than or equal to means above or on. So the graph of f is above or on the graph of g, and they are both above, okay, or on, or one is above, one is on, I don't know, it depends on this inequality right here, okay, on the x-axis. Okay, so let's take a look at this graph below. Okay, so of course right here we assume a equals 0, but this a can be anything. Okay, you just need to start. For example, if a equals 2, you just need to start from here. Okay, take a look at this part. If a equals 100, you take a look at this part. Okay, so the graph of f is above the graph of g, and they are both above the x-axis. So notice that the integral of f from a to infinity describes the area under the curve from a to infinity. Okay, right? Because we say that the area under the curve is the integral of f from a to b, right? So the area, so if you have this relationship between f and g, then the area of f, area of the region, okay, area of the region under f is greater than or equal to, okay, if f and g are equal to each other, right? Greater than or equal to the area of the region under g. You agree? Right? Take a look at this picture. The area under f is the area of the yellow region plus the area of the pink region. And the area under g is just the pink region. Okay? Good? Now, if the integral of f from a to infinity converges. So that means if this area is a specific number, then the area of G must be a smaller number, okay, or the same number if this is equal, right? So that means the integral of G from a to infinity also converges, right? Because let's say this integral converges to 5, so that means the area under F is 5. And since the area under G is a smaller number, it can be like 3 or 2, okay, that means the integral of G converges, right? Now, if the integral of G diverges, okay, so notice that right here, we are describing an area under the curve, okay, so if the area under the curve diverges, that means it's infinity. Then the area under F must be infinity, right? So that means the integral of F from a to infinity also diverges. Okay? So basically, why do we want to talk about comparison tests for improper integrals? Because sometimes we won't be able to evaluate the integral. Okay, so take a look at this right here, x over x to the 4th plus 1. Okay, to integrate this, it requires some technique. Okay, but let's say we change this to x to the 5th. Well, then we don't know how to integrate. Okay, then how do we determine whether it is convergent or divergent? We have to use the comparison test. Okay, so before we practice example 3, here we have a remark, and we will use this remark later in chapter 10. Okay, so this is really important. So the integral of 1 over x to the pth power from 1 to infinity, this integral converges when p is greater than 1. And this integral diverges when p is less than or equal to 1. Okay? Now you don't have to memorize this, but we will use it a lot. Okay, so it is my suggestion to practice this several times and then you memorize it automatically. Okay, then you might be wondering, how do I practice this? So let's say you have 1 over x squared. So the p value is 2. Okay, and then you can use power rule for integration to evaluate this integral. Right, and eventually you take the limit as this t goes to infinity, then you can get a conclusion. Right? For example, when in the case when p equals 1/2, then this is 1 over square of x. Again, you use power rule to evaluate this, and eventually you take the limit. Okay, now the only thing that is a little bit different is when p equals 1, because when p equals 1, this is 1 over x, and you cannot use the power rule. Okay, but no, don't worry, because we know the integral of 1 over x is natural log of absolute value of x. Okay, so you will still be able to integrate that. Okay, and eventually you will need to evaluate the limit. Okay, so I will leave that for you as an exercise. Okay, try to practice some values. P equals 1, p equals 2, p equals 3, p equals 1/2, p equals 1/3, and you can get a conclusion. Okay, and as I mentioned earlier, we will use it a lot in chapter 10. Okay, so after you practice this, it is my suggestion to memorize this. Okay, now let's take a look at example 3. Which one of the following statement is true about the integral? Okay, now you can integrate this. Okay, but it requires some techniques. Okay, so if you don't want to integrate this, we can use comparison test to determine whether this integral is convergent or divergent. Okay, so you might be wondering, how do I start? So notice that in order to use comparison test, you need to find something to compare to, right? So right here we have f and g. We compare f to g. right? So right here, you have x over x to the fourth plus 1. You need to find some integral to compare to, right? Then, which integral should I choose? So here's the idea. And you will see this idea again in chapter 10. So when x goes to infinity, when x is really, really large, like x is 10 billion, okay, this one really doesn't matter, right? So x over x to the fourth plus 1, when x is large, it behaves like x over x to the fourth. Okay, x over x to the fourth. So that's why I want to choose the integral of x over x to the fourth from 1 to infinity to compare to. Does that make sense? Because that one really doesn't matter. Okay, so notice that I'm not saying this is the same as x over x to the 4. No, I'm not doing that. I'm not saying that. I just say it behaves like, okay, it behaves like x over x to the fourth. Okay, so we want to find x over x to the fourth to compare with, compare to. It's okay? Okay, so right here you can see that in all these choices, we have 1 over x cubed. That is because x over x to the fourth is 1 over x cubed. Okay? Next, you want to know, you have two integrals, right? X over x to the fourth plus 1 and x over x to the fourth. You want to know which one is greater, right? You want to know f and g, which one is above, which one is below. Okay, so that's why you need a inequality right here. So you can see that in these choices, you have some inequalities. Okay, now, of course, you might be wondering, but wait, how do I know which inequality is true? So here, let's make a quick review. One half and 1/3, okay, and 3, you know 3 is 2 plus 1, okay, 1/2 and 1/3, which one is greater? Yeah, of course, 1/2, right? 1/2 is greater, but you can see that 2 is smaller than 3. This is because if we divide by a smaller number, the value will become larger, okay, so this is a smaller denominator. That means your value, your fraction, the value of the fraction will be larger. And this is a larger denominator. The value of the fraction will be smaller. Okay? So right here, you want to compare x over x to the fourth plus 1 to x over x to the fourth. You know that x to the fourth plus 1 and x to the fourth. Okay, now take a look at the denominators only. We don't care about the fractions. The denominators only. Which one is larger? X to the fourth plus 1, right? X to the fourth plus 1 is larger. So we know that a larger denominator makes a smaller fraction. So that's why you have less than right here. Does that make sense? Okay, and then because you have the same numerator, we don't have any problems here. Okay, and this is after simplification, this is 1 over x cubed. Okay, so you need a greater than. So no, greater than. Okay, so C or D. Okay, C or D. Okay, now next you have to determine whether this integral you chose is convergent or divergent. And we have to use our remarker right here. So notice that this is an integral 1 over x to the pth power. And this here, the p value is 3. Okay, the p value is 3. So we know that if we have p equals 3 is greater than 1, this means the integral converges. Okay, so right here, the p value is 3, So thus, this integral converges by the remark. Okay, so that means we have to choose D. Okay, so we talk about the first case of improper integrals. Okay, so notice that there are two different cases. In the next lecture, we will introduce the second case. Okay, the first case is when the interval of an integration is infinite. So it's really easy to identify whenever you have infinity or negative infinity in the bounds. Okay, you want to classify it as an improper integral. And the first thing you want to do for improper integral is to set up the limit. Okay, is to set up the limit. If you take a look at the old test on the 1080 website, okay, we also include the rubrics on this old test. You can see that if you don't write the limit notation, okay, then you won't get, like, you will not get a full credit. Okay, so please make sure you know that for improper integrals, the first step is always to rewrite the integral using limits. Okay, and then you just integrate as you used to do, and then eventually you will need to take the limit. Okay, take the limit. Now, if you forget how to take the limits, please find some time to review, because in chapter 10 we will do a lot of limits. Okay, we will do a lot of limits. So please make sure you know how to evaluate the limits. Okay, and on page 3 we also talk about the comparison test for improper integrals, and basically there's no techniques right here. All you need to do is all you need to know is that if I have a larger region, then I will have a larger area, right? Now, if this area is convergent, then the smaller area will be also convergent, right? If the smaller area is divergent, then the larger area must be divergent. Then that's it, okay? And we need this as well. Notice that we will use it a lot in chapter 10, so make sure you understand this, okay? And again, there are more practice problems on Canvas. Please make sure you practice all of them. There are also all exam problems on the 1080 website. Make sure you practice them as well. If you have any questions, please do not hesitate to email me. Thank you.